This video is about transformations, and it includes an introduction as well as a look at a specific type of transformation called a vertical shift. For our notes, we'll begin with a definition, and we'll say let y equal f of x be a parent function, which is a basic function whose graph can be adjusted by changing or transforming, hence the name transformations, changing its equation in several ways. Let's take a look at 5 common parent functions that we'll be using to see and perform these transformations. The first is y equals x squared. It's pretty familiar, it's a parabola, and the parent function or basic graph has a vertex at the origin at the point 0, 0. And then there are several other points that are easy to plot and useful when we're doing these transformations. Let's highlight those. So 0, 0 is a point, 1, 1 would give us a point, and then 2, 4 would give us a point, all in the positive direction. You can get those points simply by making an xy table and picking input values for x, such as 0, 1, 2, and so on. And then you'll produce, when plugging those inputs into the equation, the y values that go with them, and then those points show up on the graph. So those 3 points, and then we'll add a couple in the negative direction. The point negative 1, 1 is on the graph, and negative 2, 4 as well. Our next parent function is y equals x cubed. This function has, in the same way, a point at 0, 0, a point at 1, 1, 1 cubed is 1, and then a point at 2, 8, 2 cubed is 8. And so those basic points will reside on the positive side of x's for us. And then on the left side, or going negative, when x is negative 1, we get negative 1 as an output. So there's a point at negative 1, and then negative 2, negative 8. And so again, those 5 points will be useful for us when adjusting or transforming that parent function. Our next parent function is y equals the square root of x. This parent function has a point at 0, 0, a point at 1, 1, a point at 4, 2, the square root of 4 is 2, so you could plug in and get these points making a table, and then a point at 9, 3, and yes, plenty of points in between, but those are the easiest ones to get with nice clean numbers when making a table. And then moving on to our next parent function, which is y equals the cube root of x. This parent function has points at 0, 0, and then the cube root of 8 is 2, so we can find some nice values that way. So the point 8, 2 is there. Of course, 1, 1 is also there. The cube root of 1 is 1. And then going in the negative direction, we have a point at negative 1, and then negative 8, negative 2. And for our last parent function for now, we'll take a look at y equals the absolute value of x. This function looks like a sharp V shape with a vertex of it at the point 0, 0. 1, 1 is a point, and actually any point going in a slope of 1 upward from that works as well. So 2, 2, 3, 3. I mean, these are all nice. You can keep counting up that way. 4, 4. Anything along that line with a slope 1. Going in the negative direction as well, negative 1, 1, negative 2, 2, and any point along that slope will produce this sharp V-shaped graph. Now that we've seen some of our parent functions that we'll be transforming, let's talk about the first of these transformations called a vertical shift. A vertical shift is what you might expect it to be. We're shifting vertically. Now, to define this, let's suppose that the letter C represents some positive number. And if so, to graph y equals f of x, which is the parent function, we just listed 5 of those. The parent function represented by f of x can be shifted by adding some c value to it. So y equals f of x plus c. This will shift the graph upward c units as long as we assume, of course, that c is positive. So you're just adding some positive value to the function. The whole thing just rises upward or shifts upward. Of course, if c is positive and you subtract c from the parent function, so y equals f of x minus c, this will shift the graph downward c unit. Let's try an example where, for the following function, we are going to do several things. First of all, we're going to identify the parent function by looking at the equation of our function here. Secondly, we'll go ahead and graph the parent function, just the parent that we saw, using a dashed curve or a dashed line segment or whatever we need there. Thirdly, we're going to describe any transformations. Well, we only know about one at this point, so if we see it, we'll describe it. And then lastly, we're going to graph the transformed function using a solid curve. So after the change occurs, what does the new graph look like? Our first function is f of x equals x squared minus 3. So let's go through every one of our parts to get this example going. The first said identify the parent function. Well, by looking at this function, you want to try to spot what looks most basic to it, such as there's an x squared term first in it, which is a pretty good hint that the f of x equals x squared would be our parent function. So let's take this parent function and graph it. We'll say C graph for this, and then move over to our little graph paper grid and plot just the parent function here. Now, as you may recall, and you can refer by looking back at this, this is a parabola with several key points. 0, 0 at the origin, 1, 1, negative 1, 1, 2, 4, and negative 2, 4 as well. So with a dashed curve, I'm going to draw this parabola, which is our parent function, y equals x squared. Thirdly, we want to describe any transformations which occur. Well, thanks to this x squared minus 3, as we can see from our definition above of a vertical shift, so we'll describe our transformation as down 3. We're just shifting down 3. So then, fourthly, or lastly, we'll do that transformation and graph the new function. If you take the graph we've already plotted, the parent function, and pick every point up on it and drag it all down 3 units, you can actually do this one point at a time. You will get new points for the transformed graph. And those points are what will connect to form the transformed final function with a solid curve. So you can see the parent function in dashed and then the final function in solid, and that's how you can actually see the function moving in the process. So for part D, we'll also say C graph. Let's try another example. The second one this time has a parent function of y, or f of x, equals the absolute value of x plus 2. Let's go ahead and list each part of this. The parent function would be f of x or y. Remember, y equals f of x, so you could replace those interchangeably. But we'll say f of x equals absolute value of x. You might recall that's one of our parent functions. And so we'll go ahead and graph that parent function, looking back at the key points. There are like 2 slanted line segments that meet at the origin, forming a solid V or a sharp V shape on our graph. And we're going to graph the parent function with a dashed curve, or in this case, dashed line segments. So there's our parent function graph. Now we're going to describe the transformations. Well, as you can see from the equation, when it says absolute value of x plus 2, that plus 2 means we're going to shift up 2 units. So we'll go drag every one of the points we have already plotted and just shift them all up 2. We're not moving left or right at all, just straight up 2. And then we'll connect those new points with a solid line to form our new transformed graph.